But if you focus your attention on the crest as it moves along horizontally, you would say there is a flow, there is a movement, there is a velocity. And I'll say it again, it's not a velocity of a particle, it's a velocity of the wave. And so there's my velocity. And so the distance that it travels, and so let me just make a measurement here. Let's say I do this experiment. Let's say that I kind of imagine that these are water waves, and maybe I'm standing right here. And so here I am, maybe standing in the ocean. And I've got a little stopwatch, and right as the crest of the wave gets to me, so the wave kind of comes up and gets me wet up here to my stomach and chest area, and I go, okay, start. And I let the watch run until the next crest gets to me. I could say, well, how much distance did it travel? Well, I hope you see in the picture that if this is moving, and again, it's kind of hard to see on a whiteboard because I don't have like a video here, but if you see this thing kind of moving over, you would see then this trough get close to you, and then this crest get close to you. And so you would say, as you kind of started your watch, I'm at a crest now, and as I look back, there's the next crest. I'm going to stop my watch when that next crest gets to me. So the distance I am going to measure is one wavelength. That's really what I'm getting at. So again, standing here in the water, and I see the wave coming, I go, okay, there's one wavelength. Now, the time it would take would be what? Well, I hope you see period here. And if you remember from our last lecture, our symbol for period was this capital T. But from the perspective of the person in the water, if I just watch the water, here's what I would see. I would say, okay, the water goes high and I start my watch. And if I watch the water, it just goes down and then back up. Stop. See, that's one oscillation. The time for one oscillation is what we call the period. And the symbol we used is the capital T. And so from a perspective of not looking at the flow of the energy, just watching the water, just watching the oscillations, that one water molecule right here doesn't move left or right, it just goes up or down, then I would say it's one period, or the time for one cycle, which is the period. You might also remember that the reciprocal of the period was the frequency, or is the frequency. And so we have then a very useful equation that I want to put a box around here, because this is saying if you ever know any two of these, you can get the third. Earlier on, I was saying that I was watching a show Sunday night, and they said the wavelength was 35 millimeters. Now, I made that comment because there's a couple of neat things I can calculate knowing the wavelength of these radio waves. And one of them would be a good example here because I happen to also know that radio waves travel at 3 times 10 to the 8th meters per second. In fact, we'll have this discussion when we get into chapter 17. See, and it's because of that then I can then say, oh, all right, out of curiosity, what is the frequency of these radio waves? So 3 times 10 to the 8th divided by 35 comes out to be 8.57. And I think this was mega. 1, 2, 3, 4, 5, 6. Yeah. Times 10 to the 6th. And let me take a moment to look at the units, right? The meters would cancel off, and you would be left with this per second, which, remember yesterday, we called a hertz. I could even use the metric system here then and say these radio waves, that are communicating with Voyager out in deep space, communicating back to NASA, are at 8.57 megahertz. And so that's their radio wave communications. And in case you're wondering, if you listen to radio stations anymore instead of the internet here, but if you dial in, one of my favorite ones is the K-Earth 101, it does the classic rock. But it's called 101 because it's 101 megahertz. And so that little dial means something. And so that's or our local one, the K-Tide is 95, I drew a blank here. K-Tide is what, 95.5? No, it's KLOS at LA. 95.9? I'm looking at Ron. He doesn't know either here. Okay, but anyways, whatever the radio station is, I want to say it's 95.9, is telling you the megahertz here. I could do the same thing then if I try another one here. If you remember a moment ago, I was hitting that tuning fork over here. And as I hit that tuning fork, let me hit it again. I lost my hammer again. What did I do with it? But as I strike the tuning fork, I said that I know from earlier measurements that this piece of metal will go back and forth 256 times a second. So, if I use this nice equation, that the velocity is wavelength times frequency, I could then maybe figure out, hey, what is the wavelength of these sound waves? Because I know the frequency is 256 hertz. Now, I have to know two of these to get the third, so I need to know the velocity, and what we will learn in the next chapter is the velocity of sound at room temperature is about 343 meters per second. And so a hertz is a per second, so I'm going to be left with meters. And so I could then grab my calculator and go, 343 and divide it by 256 and get about 1.34 meters. And so I could again answer the wavelength. Now maybe I'm getting too far ahead of ourselves because we're going to talk specifically about radio waves and light waves and X-rays coming up in chapters 17 and 18. And we're going to talk a little more specifically about sound waves in the next chapter, 16. But like I said, I love this chapter because it is so powerful. It is the general property of waves, and so it's how it applies to all of these waves. But I am concerned, like I was telling you the story about X in an algebra class, if you don't see how this abstract applies to so many things, you might think it applies to nothing. And so that's the danger of being abstract. You're so abstract that students don't see how it applies to anything because you didn't say it applied to anything. So I thought you would appreciate seeing that, look, it's the same formula for all waves, and I just now applied it to radio waves, and now I applied it to sound waves, and I could apply it to water waves just as easily. And so that's the general idea. Well, a couple more things here real quick. You'll hopefully have seen that waves, when they run out of their medium, reflect. I probably don't need to show it again, but I will. You watched me make a wave. What happened when it got to the end, when there was no more rods? A simple way of saying this is if I have a rod that then moves and it is connected to a second one, it will give its energy from the first to the second. And the second one will give it to the third. And the third will give it to the fourth. So what ends up happening is all of a sudden we got the fourth one moving and these other ones have stopped. They've given all of its energy. And so that's the transmission of the energy. And so as long as there's another rod, it just gives its energy to the next one. And where it gets interesting is when we run out of rods, or if the rods are different, or if there's just something different on the other side. We'll keep this discussion kind of simple. We'll just go from rods to nothing. And so as it goes across, you'll see that instead of that last one being able to give its energy to the next one, you might do this. You might say, hey, I'm going to give my energy to, and it's like, well, there's no one. And so the rod maybe goes up a little high, and because of that, it's able to give some of the energy back to this one. It would be just like if I had started it on this side like this. And so the whole reason there is not a reflection while you're in the center of the rods is because there's this perfect symmetry between the rods on the left and the right, and it goes to here and to here and to here. But once you run out of rods, you might think of it this way, that there's nothing holding down this last one, and this last one goes up too high, and if it goes up too high, it then kind of initiates a wave back in the other direction. And so you get a reflection. But the reason I present it that way is because it's kind of fun to watch this. I'll still call it a reflection. But what if I take the last rod, and in this case, I'm going to take the last good rod. As I mentioned last time, and you can see there's two of them that have broken off from here. And so things don't work quite as well on this end. And this one's got two broken ones. One's missing and one's still there. And so the ends don't work quite as well. So what I'm going to do is make an end and take the last good one, and I'm going to clamp it here. And I want you to watch the reflection now. Because there is a reflection, but there's something different about it. And so if I make a reflection right now, did you see anything different? Did you see how the reflection was what we call inverted? And so again, why is there a reflection? Well, I was saying as the energy gets to that last rod, it goes, hey, I don't have anything to give, and it just kind of goes up. But this time, it can't go up. This time, it's stuck. And so this last rod is kind of locked into place, and the one next to it says, I'm going to pull you up. And it's going to say, oh, no, you're not. We're going to pull back equal and opposite. Right? Newton's third law. And so this last rod, instead of going too high, actually pulls down. And pulling down is exactly the same as if somebody was standing on this side and were to pull down, they would make a pulse that is dipping down instead of one that is dipping up. And so it is these forces that determine whether, when it reflects, whether or not the reflection is going to be upright or inverted. And so watch it again. I'm right here. I'm going to get a reflection, and sure enough, we go across and reflection, and it goes down. I'll show you on this big one. This one's kind of a fun one to see, because if I clamp it, and let me make sure it gets all the way clamped here. If I stand back here and make an up pulse, that up pulse will come across, and it's going to try to lift up on this spring. But it's clamped. And so the metal here, the clamp here, pulls back. And it's equal and opposite. So as this pulls back, this would be like this side going, hey, I'm going to pull down first, and that would make a downward pulse. And so you will see that my pulse, as it gets to that end, hits and inverts. I'll also point out, did you notice how I took advantage of superpositioning? Constructive interference? Well, watch it again here. And Ron, make sure you get the whole pulse back here at the beginning, because what I'm going to do is just give it a little energy the first time. And when the pulse gets all the way back to my hand, I'm going to give it a little more energy. and a little more, and the pulse will kind of build. And so I'll give it a little pulse, reflect, little more, 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 reflect. And before I damage the spring, if I stretch it too much, you'll see it was growing in energy, and I timed it just right. Oh, it's not on the board anymore, but I have constructive interference as it would flow back and forth. And then so that's our idea of reflection. Well, one more thing, and it looks like our hour and a half is up here, but I got to show you this last thing so we can call it quits to the chapter. But another neat part of, again, it's all part of superpositioning, is what if you had two full waves coming at each other, one from the left and one from the right. Now, as I had shown you, I was really making wave pulses. You know, right? I was doing this. I would say, here comes a wave and here comes another wave. And I just made a single pulse. What I want to do next and last is to say, what would happen if I made a whole set of waves? And so I have a whole set going to the right. So I'll just stand on this side and keep making it on the right. And what is approaching is a whole set from the left. And a very interesting pattern here develops. And it's a little bit hard to see. You got to kind of draw this carefully and slowly. Fortunately, it's pretty easy to make, so you're going to see this pretty well here. But right here, I'll call this the middle. Let's just say as they first get here, this crest lines up with that crest, and the superpositioning says make it really tall. Okay. And then, of course, as we come off to the side, it would say go to 0. Okay. Then we would get to the troughs, and so the trough, this would say down, and that would say down. Okay. Then back here a little further, we would get this crest with this crest. Okay, so that would say up, and that would say up. And maybe that's enough that you can kind of see the pattern. See, at that moment, as these things would overlap, right, the superposition, I guess I would call this constructive interference right now. But I probably should stay away from those terms because this is something even more interesting that we don't like to call it constructive or destructive. But right now, I would say these waves have lined up so that crests line up with crests and troughs line up with troughs. But then watch what happens a moment later. A moment later, and so if you can kind of imagine these two crests lining up, then as they move forward like this crest will line up with this trough. And at this point here, I guess I should be careful right here, let's see, so if these were right here at first, this down part would line up with this down part. And actually before it got there, I guess this going down part would line up with that going down part. Maybe I should do that one first. And as they begin to get closer, eventually this goes all the way down to 0. But an interesting pattern develops, especially a moment later, where this crest lines up with this trough. That means everywhere this has a crest, it lines up with these troughs, and everywhere this has a trough, it lines up with these crests, and so you get completely destructive interference over the whole thing. But there are some magical points that are always 0. You see this right here, when they first line up, when this crest is lined up with this crest, this place right here would be a 0 plus a 0. But then later on, as they begin to move over each other, this one begins to go down as this one begins to go up, and so that still is a 0. And so you end up seeing a very different looking pattern than what you might have thought you would get when you have two waves. Because when we think of waves, we think about them moving. We think about them traveling. And I think it's because you have one going to the left and one going to the right. Visually, you don't see anything traveling. And so that picture is, I don't know if it is very clear. I don't even know if my description of how they overlap is very clear. I think that's kind of hard and something you kind of have to work through, but it's really easy to see. And so I think the best thing I can do is show you. And so I'll go ahead and make a bunch of waves. And as I make a bunch of waves, they will travel to the end and they will reflect back. And so now I have waves going equally left and equally right. But what I hope you see here is what, to finish the chapter, is what we call a standing wave. We call it a standing wave because it doesn't look like anything's moving. I guess I should emphasize a standing wave then is a combination of this superpositioning that I was trying to get across to you and two traveling waves. So equal waves going left and right added together give you this standing wave. And this picture I have looks pretty busy, but I'm trying to emphasize at one moment in time it would look like this. And so even though I have a bunch of drawings up here, each drawing represents a different moment in time. And so I like to say a standing wave looks more like a wave that is breathing than a wave that is traveling. I'll show it again here. And so if I make, and maybe now I'll make a little higher frequency one, but I'm hoping you kind of see that same thing. That there are special places that are always at 0. You perhaps can see it even better with this long one because it fills up the whole room here. But if I take this spring over here and I maybe do something like this, get the timing just right. Okay, there we go. The wave will go down, hit and reflect back, and of course my hand is still pushing it, so I've got waves going left and right equally. And in this case there's those two nodes out there in the middle that, again, always have destructive interference, whereas the stuff in between is sometimes destructive and sometimes constructive. And so these magical points are referred to then as nodes. And so I've got a bunch of nodes. The nodes is where these two traveling waves come together and you always get destructive interference. And these other spots right in between the nodes, and that's kind of hard to draw because it's not always this point. This point then later on becomes this point, which later on becomes this point, which later on becomes that point, which later on becomes that point, which later on becomes that point. And so I don't really know how to draw this one other than maybe to put a line through there. But this point that keeps changing with time, that moves the most then, we refer to it as a anti-node. And so like I said, this chapter is abstract in the sense of the wave, but it also has a lot of definitions here. And that's really the last definition. What is a node and what is an anti-node? And now we are at a good spot. Since we know these general ideas of waves, now we're at an excellent spot to say, let's apply these general ideas to specific waves. And so for the next 3 chapters, and the next one in particular, we're going to focus only on sound waves. And so don't forget any of this stuff, because the good thing about the next chapter is it's actually a fairly easy chapter if you realize that you already know all of these things about waves in general. Now we just have to apply them to sound waves. And that's what we'll do after our 20-minute break. So let me stop here, and then we'll take our 20-minute break and come right back. I'll see you soon.